All right, number six. Number six asks which of these represents a chemical change in calcium, which is an element from the periodic table, calcium. So when we talk about physical and chemical changes, just remember that physical versus chemical. Physical, just consider these to be very easily observable. And chemical, these are not observable. These are basically the behavior around other substances. Okay, and so observable characteristics are things like color, shininess, hardness or softness, shape, that sort of thing. They can also be really easy measurements like mass or volume or things like that. But let's go through these options here. Which one is a chemical change in calcium? Melting at 842. Melting temperature, that's where calcium transforms from a solid into a liquid, but there's no real chemical change there. That's a physical property. Silvery white metal, that's just an observable color. The density, which is a measurement that combines mass and volume, that's observable physical properties. But this last one here, D, calcium's reaction with oxygen to form calcium oxide, that is clearly the chemical change here. It's calcium's behavior with another substance, in this case, oxygen, to make calcium oxide. Okay, number 7. Diamond has a density of 3.52 grams per cubic centimeter. That's the same as a milliliter. That becomes important in this problem here in a second. Just remember the volume, cubic centimeter and milliliter, they are the same volume. This question, what is the volume in milliliters of a 95 carat diamond? That is a big old fat rock. So what we want to do is remember the density equation, which looks like this, mass, density, and volume. We've worked with this since the very beginning, where density is equal to mass over volume. That's where this unit comes from, grams per cubic centimeter. That's mass over volume. And then volume would equal mass over density, and mass equals density times volume. So we're looking for the volume, this variable here, of a 95 carat diamond. So it tells us that 1 carat is equal to 0.2 grams. So let's go ahead and convert 95 carats into grams. 1 carat is equivalent to 0.2 grams. Let's see the math on that. 95 times 0.2 equals 19. So we've got 19 grams. Okay, 19 grams. That 19 grams is going to be our mass. We've been given the density in the problem, and so we're just solving for volume. Volume equals mass over density. Volume equals 19 grams over 3.52. And we've got 5.40 grams. That is one gigantic diamond. That's like as big as your thumb. That's a huge, huge diamond. probably expensive, I would guess. Okay, next one, number 8. What is the most reasonable measurement showed by this graduated cylinder? Great, so this is a significant figures problem. And I'm gonna try to zoom in here a little on this guy. So this graduated cylinder here, we would say this is accurate to the tenths place. So we've got 3 and 4 in view here. And then, so we're presuming that this is a milliliter of volume here. And each milliliter is divided into 10 little units here. So that means that it is accurate to the tenths place. which means that and remember that the tenths place is right after the decimal place. So our measurement is going to have to include the tenths place and the next one, the hundredths place. That's the way that these measurements work. And we can talk through that here. So what I like to just think about is what can you see? Like what can you see with absolute certainty here? Well, we know that this is 3 milliliters. We know it's not 4. It's somewhere between 3 and 4, but it is certainly 3 milliliters. Now we have to start narrowing it down based on these little marks. Here's our 3.5 milliliter line, 0.6, 0.7, 0.8. So the line, the graduated cylinder is showing between, let's see, 6, 7, 8, between 0.8 and 0.9. So what we can say with absolute certainty is that this is 3.8 because it's beyond the 3.8, but it's not quite to the 3.9. So this is where you take your guess at this one here. And you can put any number you want there. If you think that that's about halfway between the 0.8 and the 0.9, you could say maybe 3.85. To me, that looks a little farther along than 0.5. I'd probably call this like 3.87 or something like that. And hey, wouldn't you know it? Check it out. There is that answer right there. Now, these other ones don't. Let's go through why these wouldn't work for you. So this first one here, 3.845, we can't really take this measurement any farther than just the hundredths place. That's the whole deal behind the measuring tool. We could say 3.84, but we can't say 3.845. That's too precise based on the tool that we have to work with. So we can't have that thousandths place there. 3.8 is kind of just the other way around. We have a more precise tool than that to work with. So we have to carry it beyond 3.8, and we've got to put one more number beyond that 8. As I've explained. And then finally, D is not really a reasonable answer because even though it's the right, shows the right precision in the measurement, for 3.92, that's just off, because 3.9, our meniscus would have to be up here above the 9, which it is not. So anyway, this is pretty clearly answer C. Okay. Excuse me. Next one, number 9. Number 9. This is looking at some nuclear notation of some isotopes here. And so just remember that an isotope is just an atom, and it's just a variant of an atom. Lots of different elements, almost every element almost has multiple isotopes. And typically they're listed and written out in this way, with the number on top here being the mass, and the number on the bottom being the number of protons, which we also call the atomic number, of course. Okay, and so the mass, remember mass is always calculated by adding protons and neutrons. And so just with a little bit of algebra here, the number of neutrons is just equal to the mass minus the atomic number. Okay, and so this question is basically asking you how many neutrons are there in these isotopes, and then which two have the same number. So here our first one here is phosphorus. And this is 28 minus 15, and that gives us how many? 28 minus 15, that's 13 for this guy here. Magnesium, 12 here, so 24 minus 12, 12. So here's an example where we've got two atoms of the same element, but these are different isotopes. One of these Magnesium's has one more neutron than the other. What's the same about them, of course, is their atomic number. That number 12 there identifies this atom as magnesium. So this one has 13 neutrons. That's 25 minus 12. And so there's our 2 right there, by the way. This phosphorus and that magnesium, those guys have the same number of neutrons. They both have 12. And just for fun here, 28 minus 14. That is 14. Okay, so yeah, phosphorus 28 and magnesium 25, they have the same number of neutrons. Okay. Okay, number 10, electron configuration, everyone's favorite, although I don't think this is too tough. I would just say when you do electron configuration, reference your chemistry Bible and find this page here. Remember this, the diagonal rule. This is the sequence of sublevel filling in terms of lowest energy to highest energy, and we follow this snaky arrow diagonal line, filling in sublevels with the appropriate number of electrons as we go. Remember, those appropriate numbers are 2 in the S sublevel, 6 in the P, 10 in the D sublevel, and 14 in the F sublevel. So we'll refer back to this sequence. The other thing you can do is, like on your periodic table, that's a good one. What are we looking for? Potassium. So find your potassium. Find potassium here. It is right here, K. And I like to call this, like the battleship coordinate. Try to think about what does the electron configuration end in. Remember that these first 2 columns we call the S block. And so potassium lives at the address of 4s1. It's in the 4th energy level in the S block, and it's in the first position within that S block. So it's whatever comes before that electron configuration, it's going to end in 4s1. And when you know where it ends, then you can look at that diagonal rule, and you can basically say, okay, here's 4s right here. Zoom in here. So 4s, that's where potassium is going to end. And so we're just going to have to start all the way up here at 1s and fill in the electron configuration all the way down to 4s and make sure that we tag that little s with a 1. So here's the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And that just follows this sequence here. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. We don't have 4s2 because remember that calcium is just in the, or potassium is just in the first position in that S block. So that's what we call it, 4s1. Okay.